Hi everyone, and welcome to our lecture on the Big Bang. I'd like to open with a poem that was written in the late 1950s, early 1960s. At this point in history, a full 3 decades after the publication of Hubble's law, Hubble and Humanson's realization that the universe was expanding was still reverberating throughout the astronomical community. In particular, people debated what its implications were for the origin of the universe. And one theory, the one that modern astronomers believe to be true today, was that the universe began with a giant explosion, a Big Bang, which the poet Robertson Jeffers described as follows in his poem The Great Explosion, of which this is an excerpt. There is no way to express that explosion. All that exists roars into flame. The tortured fragments rush away from each other into all the sky. New universes. Jewel the black breast of night, and far off the outer nebulae, like charging spearmen, again invade emptiness. Okay, so let's begin with how people came to believe that this massive explosion may have occurred. It all comes back to Hubble's law, which we discussed last class. Here on the right you have a plot showing the tight correlation between the distance to a galaxy and the apparent recessional velocity, which, remember, is just the effect of the expansion of space and is not a true recessional velocity through space. This tight relationship, known as Hubble's law, has an interesting implication. Consider the corollary on the left, which shows a snapshot in time of the position of some cars on the interstate between Tucson and Phoenix. The car closest to the origin is 20 miles from Tucson and is traveling at 10 miles per hour. The second is 40 miles from Tucson and is traveling at 20 miles per hour. 100 miles and 50 miles per hour for the third, 150 miles and 75 miles per hour for the fourth, and 200 miles and 100 miles per hour for the last car. The speed is always half of the distance for these cars, which is why they lie along a straight line in the graph. If you imagine now that you can rewind time by 1 hour, as long as the cars were traveling that same speed all along, then where will they be? Think about it for a second. 1 hour ago, where will these cars be? Well, again, if you can assume that they were traveling the same speed at that time, then they'll simply be here, at half of their current distance from Tucson. So the 10 mile per hour car will only be 10 miles away instead of 20. The 20 mile per hour car will be 20 miles away instead of 40, etc., etc. And if we rewind time another hour yet, what will happen? Well, all of the cars will have been in Tucson at the start of their journey 2 hours ago. In case you didn't get it moving backwards, let me just reiterate going forward. Car 1 starts out in Tucson and travels 10 miles per hour. Therefore, after 1 hour, the car is 10 miles away, and after 2 hours, it's an additional 10 miles away, or 20 miles total. The same is true for all the other cars. The takeaway here is that when points lie along a straight line in a distance velocity plot, it implies that they started out in the same place. In my car analogy, this means Tucson, so what about the galaxy analogy? Well, this plot of Hubble's law is also a snapshot in time, the current universe. And if we extrapolate backwards, assuming these galaxies were traveling the same speed, or rather, more correctly, the universe was expanding at the same rate all along, then we have to conclude that they started out in the same place, the exact same place. This is the reason the Big Bang theory for the origin of the universe came about, because the implication of Hubble's law is that all of the matter in the universe started out in the same point in space. It's kind of a crazy idea, which is why the debate raged for many decades over the implications of Hubble's law. In fact, the term Big Bang was coined by the astronomer Fred Hoyle during a 1949 BBC radio interview. Hoyle was a proponent of the competing steady-state theory of the universe, which held that new matter is continuously created as the universe expands. Since he believed in an alternate theory, Hoyle used the term Big Bang pejoratively. But it was so cool that it caught on, and we use it today to describe the theory that the universe had an explosive origin from a single point. Hubble's law implies that there was a Big Bang, but it doesn't prove it. So today I'll focus on this big question. How do you prove that there was a Big Bang? Why has this theory been accepted by the entire scientific community? Though unfortunately a recent poll shows that 51% of the American population doubts it. I hope that by the end of this lecture you won't be among that 51%. So I'll cover just two major concepts in this lecture. First, I'll talk about the implications of the universe beginning in a single point and what we believe the universe looked like in its early days. I'll move on to talk about evidence for Big Bang cosmology. Before I begin, a caveat. As we start to get into the big questions of modern cosmology, you may become a bit frustrated at the big concepts, which can sometimes seem totally outside of the realm of human comprehension. My advice to you is simply to be patient, ask questions, and be open to new ideas. The universe is surprising, and that's a good thing. I've already hinted at this in my introduction, but let's begin by laying out the fundamental principle, the bedrock, of Big Bang cosmology, which is the idea that all of the matter and energy in the universe, all of the material that makes up you and me and all of the stars and galaxies that we see, originated in a single point. This is a shocking idea, but one fundamental law of physics, perhaps even the most fundamental law of physics, is that you can neither create nor destroy matter in the universe. So whatever we have now in the universe today was also present at the start of the universe. So close your eyes and picture that. Every person, every star, every galaxy concentrated into a single point in space. What do you expect that point's temperature and density to be? Very hot and dense, right? So here's another thing to consider. Although the earlier universe is an extreme example, we actually have a very hot and dense object that's much closer to us in both time and space, and that we can use to think about this early universe, our sun. In a hot, dense object like our sun, does light travel easily? Does light created in fusion reactions at the center of the sun fly right out of it? In other words, is the sun transparent or opaque? If you recall from a calculation that we did in class, it takes light about 50,000 years to escape the sun, rather than the 2 seconds or so that it should take to travel the sun's radius if it were transparent. In hot, dense objects, photons of light frequently encounter atoms and are absorbed. Light does not travel freely in such objects, so we say that they are opaque. In other words, you can't see through them. Since the early universe was hot and dense as well, much hotter and denser, in fact, than the sun, it was also fusing hydrogen into helium and emitting lots of light in the process, and it was also opaque. Since the universe is clearly not opaque today, what happened to change this? What do you have to do to such an object to make it transparent? Well, you mostly have to change its density, and expansion is the perfect way to do this. As the universe expands, the constant amount of matter in the universe spreads out more and more, and the density drops. This means that a photon of light is less and less likely to encounter an atom to absorb it as the universe expands. Since there's a huge amount of matter in the universe, this period of opaqueness lasted for a while as the universe expanded. At some point, it reached a low enough density that light could travel freely. It went from being opaque to transparent. So here's a cool visualization of that. These pictures are of the chandeliers at the Metropolitan Opera House in New York. They were made in 1965, around the same time as the poem I read at the start was written, when Big Bang cosmology was capturing the imaginations of everyone, including poets and artists. The chandeliers are meant to symbolize a timeline of the universe, expanding outward from a single point in time and space at the center. The dense ball at the center represents the era when the universe was opaque. Its edge, the transition between an opaque and transparent universe. Not long after this, the first galaxies form and drift apart from one another as the universe expands. So you could imagine the surface of a sphere encompassing the entire chandelier as the current universe, and its center as the origin of the universe. Based on how I described this, perhaps the abruptness of the transition seems incorrect or overblown. Shouldn't the universe have become transparent gradually? Actually, no. The universe became transparent in the instant that the temperature reached exactly the right point to allow protons and electrons to combine to form atoms. Prior to this, free electrons, rather than atoms, were what impeded photons from traveling freely through space. This moment when the universe became electrically neutral, rather than a bunch of swimming positive and negative charges, is when photons were liberated. So let's delve into the implications of this abrupt transition from opaque to transparent a bit more. In the early universe, with high temperatures and densities, lots and lots of photons were created, and these photons pinged around from atom to atom. This had the effect of homogenizing everything, so the early universe was very uniform. If the density of the universe decreased as it expanded, then how should the probability of a photon interacting with matter have changed with time? Should it increase or decrease? Well, since the instant when these photons, created in the opaque era in the early universe, were liberated from matter, the likelihood of them interacting with a particle of matter has been rapidly decreasing, and it started out pretty low to begin with. The universe had already expanded to a fairly large size by the time it cooled enough to allow protons and electrons to combine to form neutral atoms. For that reason, we expect that the universe should be swimming in photons that were liberated when the universe became transparent. These photons should make up a blackbody spectrum, since they originated in a hot, dense medium. The vast majority of these photons should have never encountered an atom since their liberation, and should be a pristine remnant of the conditions in the early universe. You could think of this light, therefore, which should be everywhere in the universe, as relic light from the Big Bang. Its existence is a natural prediction of Big Bang cosmology. So what should its wavelength be? So here's a sort of think, pair, share question that you could do by yourself. And I want you to think about it for a moment before we move on. What should the temperature of the universe have been around this transition from opaque to transparent? It might seem like an impossible question, but you actually know everything that you need to figure it out already. Think about it a moment. What should the temperature and therefore wavelength of the light emitted at this instant have been? In case you haven't figured it out yet, here's a hint. We used the sun as an analogy before, and it can work here again. Does light travel freely through the sun? So what should the temperature and density of the universe had been at that instant when this relic light from the Big Bang was released compared to the temperature of the sun? The universe had to reach a temperature of 3,000 Kelvin, cooler even than the coolest stars, before light could travel freely through the universe. Since that time when this early light was emitted, the universe has been expanding all along. And just like all other forms of light, this relic Big Bang light is subject to cosmological redshift. As the universe has expanded, its wavelength has been stretched out. The Big Bang relic emission, as we just found, started out at a temperature of 3,000 Kelvin. If we plug this value into Wien's law to find the peak of the blackbody spectrum of the early universe, we get a value of 1,000 nanometers. As you may recall, the longest wavelengths of visible light are about 700 nanometers, so this relic emission originally peaked in the infrared regime. But the universe today is 1,000 times bigger than it was then. So the wavelength has been stretched out by a factor of 1,000 by the expansion of space. 1,000 nanometers times 1,000 is 1 million, or 10 to the 6th nanometers. That's where the spectrum should peak, but since 1 nanometer is 1 billionth of a meter, or 10 to the minus 9 meters, that gives us 10 to the minus 3 meters, or about 1 millimeter, for the peak wavelength of this emission. Again, all I'm doing there is just transforming 1 times 10 to the 6 nanometers into millimeters, and it's about 1. This means that the apparent temperature of the black body has also decreased by a factor of 1,000 as the universe expanded, from 3,000 Kelvin down to about 3 degrees Kelvin. Of course, this simple math surrounding the factor of 1,000 expansion comes from a modern understanding of the expansion rate of the universe. But at the time that this relic emission was first predicted, scientists didn't know precisely how much the universe had expanded. They knew that they should be looking at wavelengths longer than 1,000 nanometers for the emission, but they didn't know precisely where. And in the end, this relic light was discovered by accident. In the mid-1960s, a group led by Robert Dicke at Princeton University set out to find this relic light from the Big Bang. Just 30 miles down the road from Princeton, at Bell Labs, the physicists Arno Penzias and Robert Wilson were working on developing early communication satellite technology. This involved bouncing radio signals off of balloon-borne communication satellites and picking them up with a very sensitive radio antenna. In order to do this, Penzias and Wilson had to very carefully study and remove all of the sources of background noise in their signals. They were able to get rid of contamination from nearby radar installments and radio broadcasts. They cooled their detector down to 4 degrees Kelvin to get rid of radio photons emitted by the warm detector. But they found that there was still a persistent noise in their data. They saw it both day and night, and it was uniform across the sky. They even resorted to cleaning all of the bird poop off of their antenna as a possible noise source until a colleague told them about a research paper by the Princeton group predicting this pervasive background radiation left over from the Big Bang, and that it would be found at microwave wavelengths. The Princeton group had been preparing their own search, but they were scooped. Penzias and Wilson had inadvertently discovered the relic light from the Big Bang, which we call the cosmic microwave background. They won the Nobel Prize in 1978 for this discovery. This relic light, as we found before, peaks at about 1 millimeter, which is well into the microwave regime. So that's why we call it the cosmic microwave background, or CMB. So now that we have a name for it, let's summarize and then delve further into its properties. First and foremost, the CMB was emitted at a time when the universe was much simpler than it was today. The entire universe was a uniform, uncontaminated black body. There were no heavy elements or cool patches to contaminate the spectrum, so we expect it to be very smooth. Since it was originally emitted at 3,000 Kelvin, it originally peaked at 1,000 nanometers, just redward of the visible light spectrum. As the universe expanded, cosmological redshift moved this peak to longer and longer wavelengths until it ended up at about 1 millimeter, 1,000 times longer than where it started. We expect it to appear in every direction, but to be relatively faint, because as the universe expands, you're spreading the same amount of CMB light into a bigger and bigger area. In other words, the CMB luminosity has remained the same, but its flux has decreased as the universe expanded. So let me list some of its properties. The CMB is a perfect thermal blackbody, as perfect as we see in nature, which you can see from the CMB spectrum on the right here. That's real data. It was emitted in the early universe at the instant when protons and electrons were free to form neutral atoms and light was able to travel through the universe. The universe was perfectly uniform at that point because every piece of it was in contact with every other piece through the exchange of photons and other particles. The CMB was emitted when the universe was uniform, and very, very few CMB photons have ever interacted with matter since it was emitted. So it's nearly perfectly uniform and isotropic, which means the same in all directions. Lots of things on Earth inadvertently pick up CMB photons due to this isotropy, this uniformity in all directions. In fact, 1 to 2% of the static on your TV is due to CMB photons. Another critical thing about the CMB is that it has the longest look-back time possible for light. Because the universe was opaque before the CMB was emitted, we can never look farther back in time than the instant when the CMB was emitted, which was at a redshift of about 380,000 years after the Big Bang. Even with the factor of 1,000 expansion of the universe since it was emitted, there are still a lot of CMB photons out there, about 400 million per cubic meter in the universe, which means that CMB photons outnumber atoms in the universe by 1 billion to 1. In fact, CMB photons are by far the dominant type of particle in the universe. There are more CMB photons bouncing around than have ever been emitted by every star and galaxy in the entire history of the universe put together. A final property of the CMB is that because of its perfect blackbody nature, the CMB has a very precisely measured temperature of 2.723 plus or minus 0.0010 Kelvin. This is the temperature of so-called empty space, although it's not empty of CMB photons. If you found yourself out in the void of empty space between galaxies, CMB photons would keep you a roasty-toasty 2.723 degrees Kelvin. Okay, so back to the question that I posed at the beginning of the class. How do we prove that there was a Big Bang? Well, as you've just learned, the evidence is literally all around us. Every one of the properties of the CMB that we described is consistent with Big Bang cosmology, its uniformity, its long wavelength. The universe is swimming in evidence of the Big Bang. Here's something interesting to think about to put the flux of CMB photons into perspective. Here on Earth, there are as many CMB photons falling from the sky as there are photons emitted from the full moon. So if we humans had microwave eyes, you could walk outside any night of the year and see shadows cast by the light of the Big Bang, the light of creation. Kind of makes you want to have microwave eyes, doesn't it? Penzias and Wilson made the first images of the CMB in 1965 with their microwave antenna at Bell Labs in New Jersey. Since then, NASA has launched 2 telescopes with the express purpose of mapping the CMB at higher resolution. First, the Cosmic Background Explorer, COBE, in 1992, and then the Wilkinson Microwave Anisotropy Probe, in WMAP, in 2003. That one is a mouthful, and I'll explain what it means in a minute. First, let's start with a low-resolution image of the CMB. If we look at the sky from 0 to 4 degrees Kelvin, meaning we assign the color red to 4 Kelvin patches and blue to 0 Kelvin patches, we see this. The CMB is exceptionally uniform at this level, like the Earth's blue sky is on a perfectly cloudless day. If we want to see any small fluctuations in it, what we call anisotropies, or non-uniformities, then we'll have to play some tricks with the contrast and stretch of the image around the value of the CMB temperature, which we know to be about 2.7 Kelvin. For example, I could take this image of my cat looking grumpy in a Santa hat and play with the stretch, which means pick different pixel values to be the high and low colors, and change the contrast between those colors. I can bring out different features by doing this. This is kind of like how they pull information out of sound clips in shows like CSI by subtracting or filtering out background signals or honing in on certain frequencies, though this example is slightly more realistic. So if you zoom in on so that you're looking at temperatures very close to 2.7 degrees Kelvin, what do you see in the cosmic microwave background? Well, if you change your stretch to cover just 0.008 Kelvin, 0.004 Kelvin on either side of the known peak of the CMB, you see this. Here, red is very slightly warmer sky, 2.732 Kelvin, and blue is slightly cooler, 2.7274 Kelvin. Sorry, 2.274 Kelvin. What you're seeing is actually a Doppler effect, but since this is a temperature map, red and blue are reversed relative to what you would expect when I say Doppler effect. The motion of the sun around the center of the galaxy means that we have a velocity of 370 kilometers per second relative to the CMB. This is a very small effect on the 0.004 degree Kelvin level, so we don't see it unless we can achieve contrasts like this and pull out very small effects. This is a good review of both the Doppler effect and Wien's law, so let's spend one more slide explaining it. What you actually see here is the sky appearing red or a little hotter in the direction that the sun is traveling relative to the CMB. This is due to the CMB photons in that direction being slightly blue shifted, because the sun is moving towards them. If that seems backwards to you, remember that it doesn't actually matter which object, the source or the observer, is moving to see a Doppler effect. Only the relative motion matters. Our motion towards the CMB in one direction of the sky results in a blue shift, which means the CMB appears with very slightly shorter wavelength in that direction. That's been colored as a warmer temperature even though it's blue shifted, because shorter wavelengths actually mean higher temperatures, according to the inverse proportionality between wavelength and temperature in Wien's law. As one increases, the other decreases. So shorter wavelength, blue shifted, means higher temperatures. The red region in the CMB image is the part of the sky that the sun is moving toward, and the blue is the region it's moving away from, where the light is a little red shifted and so apparently cooler. The signal is well understood, and we can remove it easily and delve even deeper into CMB non-uniformities, or anisotropies. The next thing we see when we subtract the Doppler signature from our motion relative to the CMB is a warm stripe right along the plane of our galaxy. This is another very small signature, just 0.0002 Kelvin, and it's actually a result of contamination from sources within our galaxy, lots of which emit microwave radiation. If we subtract that signature as well, we're left with this. This image shows anisotropies, or non-uniformities, in the CMB on the micro-Kelvin level. These are very, very, very small temperature fluctuations that we see by adjusting the contrast of our CMB image to exaggerate very small differences, and which we also only see by subtracting the Doppler signature of the Earth's motion relative to the CMB and the contamination from sources in our galaxy, both of which are larger effects. These cold and warm patches are only colder or warmer by 1 part in 100,000 or so, which means that the CMB is smoother than a billiard ball. If you look carefully at these anisotropies, you can see that they're not very well resolved in this image, which was taken by COBE. This image is actually the reason that WMAP, the Wilkinson Microwave Anisotropy Probe that I mentioned earlier, was launched, to find out how big these patches in the sky really are by taking a higher resolution image. So here's the WMAP image, which did the same thing with smaller pixels. This level of fluctuation is the same in every direction and is not due to any known source, so we believe it to be intrinsic to the microwave background. In other words, it tells us something about the conditions in the instant that the CMB was emitted. What is that, do you think? What would the CMB look like if the universe really had been perfectly uniform at the instant it was emitted? Which of the signals that we just pulled out would still be there and which wouldn't? Well, the signatures of the Earth's motion and the plane of the galaxy would still be there, but you'd expect this patchy image to look more like our original image if the explosion really had been uniform. Now, lest you think that this throws everything I've been saying out the window, keep in mind that this is an extremely small degree of anisotropy. The CMB is patchy only on the micro-Kelvin level, so it's pretty uniform, but not perfectly so. Which means that the Big Bang was also not perfectly uniform. It was patchy at a very, very, very low level. 1 part in 100,000. This turns out to be an exceptionally good thing for us, the non-uniformity of the Big Bang. If the Big Bang had been perfectly uniform, and every particle in the universe were equally spaced with every other, then every particle would attract every other in a perfectly balanced way, and nothing would ever collapse under gravity. You'd have no stars, no galaxies, and by extension, no people. We owe our existence to the non-uniformity of the Big Bang. So this patchiness or anisotropy in the CMB is perfectly consistent with our understanding of the Big Bang and with our own existence. So let's go back here for a moment to a very simple picture of the universe with the CMB added. The opacity of the early universe places a practical boundary, if not a physical boundary, around us. We can never see back farther in space than the instant of the CMB's emission. We can never see back farther in space than the instant of the CMB's emission. We call this surface between the transparent and opaque universe the surface of last scattering, because it's the last time the CMB photons interacted freely with matter before traveling out into the universe. This makes it the edge of the observable universe, though there's one more hidden signature in the CMB that reveals it's not a physical edge. Cosmologists have long believed in a so-called inflationary cosmology. This is not contradictory to, but is rather an additional piece of Big Bang cosmology. The basic idea is this. After the Big Bang, the universe expanded normally for a while, but it underwent an epoch where it blew up very quickly, with space in fact expanding faster than the speed of light. This is possible under physical laws because space itself is not limited in the speed with which it can expand. Only objects within space are subject to this limit. This extremely rapid inflation ended very abruptly, sending something called a gravitational wave reverberating through space. Gravitational waves are something that physicists have long believed exist, and we unfortunately don't have time to cover them in any detail in this class. Suffice it to say that gravity waves, from an extreme event like inflation, should reverberate through the entire universe, just like the CMB. But up until very, very recently, we were not able to detect any signatures of gravitational waves. Enter a telescope called BICEP 2 at the South Pole in Antarctica, which just recently completed a very careful polarization map of the CMB. Polarization is an additional property of light, something that we can measure in addition to the wavelength, although the specifics of it are outside of the scope of this lecture. And inflation, or rather the gravitational waves sent off by inflation, are expected to have given the CMB polarization signature a very particular pattern. To summarize very briefly, a regular density wave like sound should induce a polarization pattern called an E mode, which looks like the top right panel. And a gravity wave should induce a curly-cued circular polarization pattern called a B mode, which is in the bottom right panel. So here's BICEP 2's map of the polarization of the CMB. Imposed on top of the red and blue anisotropies that we've already discussed is a curly-cued B mode polarization pattern. We know of no other way to create these besides gravitational waves, and the uniformity of the signature tells us that it must have occurred in the early universe. This is the most convincing evidence to date that inflation happened. There's also some anecdotal evidence related to how apparently flat the universe is, and that we'll talk about in a later class. For now, keep in mind that all evidence indicates that an inflationary epoch did occur in the early universe, before the emission of the CMB, and this means that the observable universe, observable that is from our location, is probably much, much smaller than the universe as a whole. No matter how long we wait, there are parts of the universe whose light will never get to us no matter how long we wait, which means the universe is bigger even than cosmology pioneers like Hubble ever imagined.